In our final section, 8.4, we'll study the binomial theorem. This is the development of expressions in the form x plus y to the n using either patterns or formulas. But before we get right to that, we need to talk about Pascal's triangle, which is the template you see to the right here. I'm going to talk about two ways to build it, one using combinations and one using patterns within the triangle. So let's dive right in. If we look at the first three rows of this triangle here, or I guess up to the fourth row, what we're going to notice is we've written out 0, choose 0, and then 1, choose 0, 1, choose 1, then 2, choose 0, 2, choose 1, 2, choose 2, 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3, and so on. And so we're just going to evaluate these right now. I'm not doing anything fancier than that. I'm just evaluating what is 1, choose 0, and what is 1, choose 1. Well, those are both 1. And then what is 2, choose 0, 2, choose 1, 2, choose 2, and we get the numbers 1, 2, and 1. And what are the values of these four expressions? And there we go, we got 1, 3, 3, and 1. Okay. So how do we fill out a row in Pascal's triangle using the NCR term? What we do is we set the lower subscript value, which we're going to call n, to be 1 less than the row number. Well, I mean, if you've been following the 0, 1, 2, 3, you're probably just thinking, I'm just going to make it the number that comes after 3, which is 4, and that's exactly correct, right? So it happens that the first row started at 0, so if I said, what is it for the fifth row? It's 1 less than 5, it is 4, but you might just be following it's, 1 more than it was in the previous row. So we get this 4 choose something. And then the right subscript, which we're going to call r, is just going to start at 0 and work its way up to the highest possible value, which will be once it reaches n, the left subscript value. So if I put 4 choose 0 in my first spot, then I would just start counting. 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. And if in my sixth row, when n is 5 here, the left subscript is 5, I would again start with my right subscript at 0 and count up. So 5 choose 0, 5 choose 1, 5 choose 2, up to 5 choose 5. Great. Well, these are values that you could determine in your calculator, but I want to show you that there's another way now to view this triangle, or to calculate the values of the triangle anyway. If I look at the row, let's say 1, 2, 1, so this third row here, what I notice is each of the three numbers has numbers above it, of course, the previous row. Now, on the leftmost number, this 1, there isn't really a number in this yellow spot here, so it's just the 1 that's above it. So this pattern is going to be true, but it doesn't look exactly the same as what I'm about to show you. But in the middle number, this 2, you can see that it has two values above it, that 1 and that 1. And they add together to make the 2. Okay, let's jump down to the next row here. If I look at this next row, again, you see that on the edges, the 1s only have one number above them. But when I get to this middle spot, it's the addition of this 1 and this 2 that make this 3. And the addition of this 1 and 2 that make this 3. All right, so without evaluating all of our 4 choose 0, 4 choose 1, 4 choose 2 terms in the next row, how could we figure these values out? Well, on the edges, they only have the 1 above them. What would it be in this next spot? Look at the two values above it, add them together, and what do you get? You get 4. What would the value be in this middle position? Well, I've got two 3s above it. They add up to make a 6. And with this, I'm able to figure out all the values in that next row. And this holds true for the one following that, right? Bring the 1s down. 1 plus 4, 4 plus 6, 6 plus 4, 4 plus 1. And suddenly, I've got Pascal's triangle. Now, we've seen two ways to do it. You can add up the numbers from the previous row, or the two neighboring numbers from the previous row to find the value below them. Or we can use our NCR notation, so 5 choose 0, up to 5 choose 5 for that row, and depending on the row value. So let's say I'm asked now to list all the values for the 7th or 8th row. Because I have this 6th row, and just to remind you again, in the 6th row, n is 5. So think that through. The 6th row, n is 5. What's n going to be in the 7th row? So in the 7th row, where I have n is 6, I'm going to start at 6, choose 0. Okay. But because I already have the values laid out, 1, 5, 10, 10, 5, 1, I'm just going to use those numbers and add up the two above each spot. So 1 plus 5 makes 6, and 5 plus 10 makes 15, 10 plus 10 makes 20, 10 and 5 makes 15, and 5 and 1 makes 6. Notice Pascal's triangle is always symmetric, right? So what I start going in with, 1, 6, 15, then 20. Oh, I've hit the middle. Now I go back out, 15, 6, 1, right? In that same values every time. And then the 8th row, same idea. Adding up all those values, I get what I do. But I want to highlight again that in the 7th row, where are you here? The 7th row, we started with 6, choose 0, right? So n was 6. And in the 8th row, we started with 7, choose 0, and so on. And the reason that's important is, even though it's probably a lot easier to just take the sum of the two terms above, it's not going to help us if I ask you for a later row. Like, let's say I asked all of a sudden for the 11th row or the 14th row. Well, you would have to write out all the rows that come before the, say, 14th row before you could tell me what was in the 14th row. Whereas when we use our NCR pattern, right, when we use this notation here, if I said the 14th row, you could just say, oh, that's when n is 13. And then you could just start writing out your terms, 13, choose 1, up to 13, choose 13, and evaluate them all to complete the row. So we want to know that both of these patterns exist, but we're really going to lean into this top one here. Okay, so let's talk about a more general row number now. So instead of saying the 7th row or the 8th row, let's say the n plus 1th row. N plus 1th row, what's that? Yeah, a little bit weird, right? Why wouldn't we just say the nth row? The first, the second, the third. Well, the reason we don't do that is we'd get a problem right away. In our first row, if we were just saying the nth row, then that would mean that our n value was 1. But it's not, it's 0, right? Oh, okay. Well, then when it's 0, why can't we just say the 0th row? Well, that's not really a thing we do, because when we're counting rows, we use the natural numbers, right, which start at 1. So, because of this, let's say, disagreement between n, who wants to start at 0, and the row number, who wants to start at 1, we need to consider the row number to be the n plus 1th row. Great. So, notice the pattern. First row n is 0, second row n is 1, third row n is 2. There's a difference between the row number and the n value, and it is 1. So, we've described all these numeric ones. What would this be then for the n plus 1th row? Well, the n plus 1th row, remember, the left subscript value is 1 less than the row value. The n plus 1th row would start at n, right? I know that might be a little bit weird. So n plus 1, that's your row value. 1 less than that is n, so that's what we're going to have as our left subscript. So it's going to be the row that goes n choose 0, n choose 1, n choose 2, and it's going to keep going until we get to n choose n. So here's our first term in the row, and here's our last term, and then we just fill in all the other values. Now let's use these patterns to state the first 3 terms of the 25th row. All right, now I want your brain to split for a moment. You're either going to be asked to discuss terms in the 25th row, or you're going to be asked to discuss terms when n is a certain value. And usually in that case, you'll just be shown the first terms. They'll say, what are the next few terms? But if it's a 25th row, be careful. That does not mean n is 25, right? It means n is 24. So our first terms are 24, choose 0, because we always start at choose 0. And then 24, choose 1, and then 24, choose 2. Now, we want to actually give the numerical values for Pascal's triangle, so grab your calculator and evaluate these three. We get 1, 24, and 276, and then those would be the start. Remember, that means those would also be the last three of the row. So if this is 24, choose 0, it would also be 24, choose 24. If this is 24, choose 1, it would also be 24, choose 23, right? The term before the last one. And this, if this is 24, choose 2, it would also be 24, choose 22. So know that we don't, have to do every term, because we only need to do half of them, and we'll have all the other ones, just because that's how the pattern works. All right. I want to put a star beside this last bullet of the warm-up. It asks us to predict the number of terms that will be in the 25th row. Okay. In the first row, we see there is one term. In the second row, we see there are 2 terms. In the third row, we see there are 3 terms. This seems like a pretty easy pattern to observe. The number of term matches the row numbers. So in the 25th row, we would have 25 terms. But I want you in this moment to not say, oh, that's so easy, I'll definitely get that right if ever asked. I want you to recognize that there are 25 terms when n is 24, right? So that means the 25 terms are the terms from 24, choose 0, up to 24, choose 24. Oops, 24. Okay, because if you do this too quickly, you might just think, oh yeah, when it's 25, I have 25. No. Because we are counting 0 up to 24, it's one more than 24 terms, right? So just remember that. The number of terms is one more than the n value. And that is the row number. But I find that often later we're talking less about the row number and more about the n value. So connect the number of terms to being one more than the n value. Great, and that's how you build Pascal's triangle.